Okay, so as discussed on Monday for the next, for this lecture, actually, we're going to go through some of the key concepts behind classical optimization, so nonlinear optimization problem, where we solve over a finite amount of decision variables. And the idea here is not that this is a class about optimization, this is a class about optimal learning-based control, but many of the insights from classical optimization carry over to the field of optimal and learning-based control. So in particular, what we did on Monday was to define what a nonlinear optimization problem is and what does it mean for a point or a vector. I will use this terminology interchangeably to be a local minimum or a global minimum of a given objective function f. What we're going to do now is a couple of things. So first, derive basic necessary conditions for optimality. So these are conditions that essentially say if a given point or vector is a local minimum, then something has to happen. And typically people use these necessary optimality conditions, for example, as filters to filter out candidates for optimality. The fact that you fulfill a necessary optimality condition doesn't guarantee that that point is a local minimum. But if it does not fulfill, but if a point does not fulfill that necessary optimality condition, there is not a chance that that point can be a local minimum. So how do we derive necessary conditions for optimality? So the idea is that you assume that you are at a local minimum, and you see whether there are any particular insights that you can derive from the fact that a point is a local minimum. Particularly, the idea is to reason in terms of what happens when we perturb a local minimum, denoted as x star, by a small perturbation delta x. And we try to find some general rule that can serve as our necessary optimality condition. Specifically, from basic calculus, we know that if f is differentiable, f of x stars plus delta x, where delta x is a small displacement, so you're just moving a tiny bit out of x star in some direction, is approximately equal to f of x star plus gradient of f evaluated at x star times delta x. Prime means transpose. So you should be familiar with this notion. Of course, there are some error terms here, but the idea is that as delta x gets closer and closer, the first order term, so the term that includes the derivative, becomes the dominant one, and so the other terms can be neglected. And so, roughly speaking, we can look at this approximation as it being an equality. Okay. Or one can go one step further and consider a second order approximation where in addition to the first order term, you also account for a second order term. This is the Hessian of the function f, so basically the matrix that collects the second order derivatives. Are you okay with this? Yeah.
Are you taking the gradient over the derivative of f, or is it you're taking the gradient over f, the function f?
Oh no, gradient of f is just notation. So this is the nabla symbol. So by definition, nabla f is defined as the vector of the derivatives with respect to each variable. Oh, yeah. x2, dot, 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 derivative xn. This one? Oh yeah, just transpose. It could be like T, or here in this class I use other transpose, or to denote the transpose in this class I will either use the symbol capital T or prime. Yeah, same thing here. Okay, so far nothing particularly interesting. Now, let's apply the fact that we are assuming that the X star is a local minimum. So if X star is a local minimum, by the definition of a local minimum, if I move around that point, the function f has to assume a larger value. This is by definition for a point to be a local minimum, which means that f of X star plus delta X minus f of X star has to be greater than or equal to 0. This is because we're assuming that X star is a local minimum, which means that if we move around, then the function f has to take on a larger value. But if this is the case, and assuming that delta X is small, so this relation can be taken as an inequality, so this implies that remember that f of X star plus delta X minus f of X star is equal to the gradient times delta X. So that implies, worse. This implies that the gradient of f evaluated X star times delta X has to be greater than or equal to 0. I write this scalar product in expanded form, so I carry out the product. So this implies that the summation from I equal 1 to n of the partial derivative of f with respect to xi times the delta xi is greater than or equal to 0, where the delta xi are the displacements with respect to each ith coordinate. So delta x is a vector with displacement delta x1, delta x2, delta xn. Any questions about that? So remember that if X star is a local minimum, then f of X stars plus delta X has to be greater than or equal to f of X star for all possible delta X, small enough. That is for all possible delta X. Let's just fix a few possible choices for the delta X. So let's consider displacement of the type delta X equal to epsilon, where epsilon is a small scalar positive number. Say 1, 0, 0, 0. So this will be, say, delta x1, or another possible choice for the vector delta x could be delta x2 equal epsilon, where all the coordinates are 0 except the second one, and so on. So this is just a specific choice of delta x. This relation has to be true for all possible choices. I'm just selecting a few possible choices. But if I select delta x in these ways, and then I carry out the scalar product, you'll see that all those products are equal to 0 except for the ith coordinate. So if I start plugging in all these possible choices of displacements, I start getting conditions of the type epsilon delta partial derivative f with respect to xi times 1 greater than or equal to 0. But I also can take the negative of this one. So I get minus epsilon partial derivative f with respect to xi times 1 less than or equal to 0. Epsilon is a small positive number. So this, I can just cancel it out from this inequality. So essentially, I get a bunch of inequality of this type. So wrapping up, we have found that if x star is a local minimum, then each partial derivative has to be simultaneously greater than or equal to 0 or less than or equal to 0. So what is the only number that is simultaneously greater than or equal to 0, less than or equal to 0? 0. So basically, we've just proven that each partial, if x star is a local minimum, then each partial derivative of f with respect to xi has to be equal to 0. Putting all those results together, we get to the celebrated necessary optimality condition that says that at a local minimum, if X star is a local minimum, then the gradient has to be equal to 0. Pictorially, in the one-dimensional case, say that you have a function like this one. So this is a local minimum. And indeed, you see that here the derivative is equal to 0. Here, the derivative is equal to 0, but this is clearly not a local minimum. This is a local maximum. So that shows that the fact that the gradient is equal to 0 is a necessary condition for optimality, but is not a sufficient condition for optimality. And probably you already know about this, but my point here is just to reiterate the concept of a necessary optimality condition, because as I said, it will become quite useful as we move on. Now, of course, we can go one step further. So far we have used a first order approximation of a function, but we can also use a second order approximation of a function and see whether the fact that the point is a local minimum tells us something about a function beyond just the first order derivative. Well, remember that the second order approximation of a function reads like the following. So you have a linear term and a quadratic term. Quadratic because the delta x multiply each other. So by the same reasoning as before, if x star is a local minimum, this difference has to be greater than or equal to 0, which means that this term also has to be greater than or equal to 0. But we have just proven that at the local minimum, the gradient is equal to 0. So we are left with the fact that if a point is a local minimum, then this quadratic product has to be greater than or equal to 0. A delta x is arbitrary. It can be, so for example, if you're in 2D, it can be any vector in any possible direction. So what is this telling us with respect to the Hessian of the function? There has to be positive semi-definite. Actually, that's a definition of a positive semi-definite matrix. So if the function is twice differentiable, we get the strengthened necessary optimality condition that not only the gradient has to be equal to 0, but the Hessian has to be positive semi-definite. Which leads us to the NOC theorem, necessary optimality condition theorem. Let x star be an unconstrained local minimum of a function that maps a vector of n variables into a scalar that is a real number. R is the set of real numbers. Rn is the set of vectors with components in the real space. Assume that f1 is C1. C1 means that the function is differentiable, is continuously differentiable. And let's assume that x star is an unconstrained local minimum within an open set. Then the gradient has to be equal to 0. And additionally, if f is twice differentiable, the Hessian has to be positive semi-definite. As a reminder, an open set is, loosely speaking, a set that contains a ball around each point. So basically a set that doesn't contain its boundary. This is important because, for example, say that you have a function that is defined between A and B. Is this point here a local minimum? Well, it is, right? So if you move in any allowable direction, then the value of the function increases. But is the derivative equal to 0? Clearly not, because this will be the derivative. So here what's happening is that this point is not inside the open set. It's indeed on the boundary. So this necessary optimality condition only holds if you're not on the boundary of the domain of your function. So that's what the open set statement here is referring to. If you're within the open set, yes, then if there is a local minimum, then the derivative has to be equal to 0. Yeah?
So when You say the open set, does that mean the same thing as unconstrained?
No. So if basically, so here, so you can have like an interval like this one, right? So the interval does have constraints, so has a lower bound as an upper bound, but does not contain its boundary. So it's the notion of an open interval or closed interval. Does it make sense? Basically, you don't want to pick points that are on the boundary of your domain. That's what it's saying.
Unconstrained problem.
If they are constrained, that's perfect. Then, of course, the space of real numbers doesn't have a boundary, so yes, you're in an open set. And so this holds true, no problem. This is more for the case of a function that, for example, is defined in the maps all numbers from A, B into the real numbers. So the domain is actually between A and B. You want to make sure that you apply the NOC condition only for points strictly between A and B. Otherwise, you might get a spurious situation whereby you have a point that is a local minimum, but is not, doesn't have a derivative equal to 0. That's all I'm saying. But the moment you move away from the boundary, then for a point to have any chance to be a local minimum, then the derivative has to be equal to 0. This is more of a technicality, by the way. So then a natural question is, can we strengthen this to a sufficient optimality condition? So a condition that says, if something happens, then that point is a local minimum. And here I'm just going to give you the intuition. Say that now we strengthen the condition whereby the Hessian now is not just positive semi-definite, but is positive definite. Which means that as you move locally around X star, the value of the function increases. So this suggests that strengthening the condition Hessian to be positive definite would lead us to a sufficient optimality condition. Of course, the proof has to be a little bit more involved because there are some additional terms that were not accounted in the approximation. So we should use a little bit of limit arguments to make sure that this actually is mathematically rigorous. But the intuition is that if the Hessian is positive definite, the gradient is equal to 0, the function locally around X star is essentially a ball, right? And so the value of the function increases immediately after you leave X star, which means that the Hessian being positive definite is indeed a sufficient condition, which is encapsulated in the theorem here. So for example, one way to use these conditions is that you look at all the points for which the gradient is equal to 0. And then maybe you get 6 points that satisfy the condition. And then you evaluate the function at each one of these points. And then you apply some other argument to see whether that is indeed the local minimum or not. One special case that will become important later is that of a convex function. Probably you already know what a convex function is, but just in case you don't know about it, it's a specific class of function that in a way have a behavior that is very nice, and then I will specify later what I mean by nice. But they're still nonlinear functions. So how are convex functions defined? So let's start from the domain of a convex function. A convex function is defined over a convex domain. What is a convex domain? Well, a set is said to be convex if whenever you pick 2 points, the line joining them is contained in the set. So this is a convex set. Mathematically, a subset of the Euclidean space is referred to as a convex set if whenever you pick 2 points x and y, the line joining x and y is contained in the set. So this set is convex. This set is not convex, right? Because if I pick these 2 points, then this line leaves the set, which means that this set is not convex. So let's consider a set C, which is convex. A function f is called convex if this condition holds. What does this condition say graphically? So let's just draw a diagram. Yeah. So you have a function. So you have x, you have y, and then you have a function such as this one. So you pick any point between x and y. So for example, this point here. So this will be alpha x plus 1 minus alpha y. This will be f of x. This will be f of y. So the function is convex if the line segments between any 2 points on the graph of the function lies above the graph. So this will be the segment that joins fx and fy. The function is convex if that line is above the graph of the function. So for example, this function is convex. And then this function, what do you think? Is not convex. Because for example, if you pick 2 points, then the line will be below the graph. So you might say, why do you care about such functions? From the point of view of optimization, you care for 2 reasons. So these functions are special in that a local minimum of f over c is also global minimum. In general, nonlinear optimization, a local minimum is not guaranteed to be a global minimum. You might have many local minima, and then some of them will be global minima. In addition, if f is strictly convex, which means that this inequality holds strict for all points not in the boundary, then there is at least, at most, 1 global minimum. Even more interestingly, if f is convex and is differentiable, then the gradient being equal to 0 is a sufficient condition for a vector x star to be a global minimum of C. So this is nice on 2 different accounts. Not only gradient equal to 0 is a sufficient condition, as opposed to just being a necessary condition, as it is the case for general nonlinear function, but also is a sufficient condition not just for local optimality, but indeed for global optimality, which is great because essentially means that a very local test, so essentially taking a gradient means that you're just looking at a function very locally, tells you something, a property about the entire function. So you can think how computationally convex functions are much easier to deal with. That's basically the intuition I want to give here. Yeah?
You mentioned if the convex function is differentiable.
Yeah.
How do convex functions differentiable?
Yeah. For example, if you have a kink. Yeah. Okay, so we'll get back to this later. In particular, one of the strategies we look at to compute trajectories, to solve open loop optimal control problems, will be to successively convexify a function, solve a convex optimization problem, get a new solution, reconvexify the problem, and iterate. It turns out that this strategy is one of the most popular strategies to do trajectory optimization for robotic systems of all sorts. So we'll come back to convex optimization later. So that's essentially what I wanted to say about necessary optimality conditions. They are useful to filter out the candidates. They form the basis to derive a computational algorithm to compute local minima, as we will see in a second. They can also be used for sensitivity analysis purposes, so to see how much a local minimum might change if we change some of the problem data, like some of the value of the parameters in your problem, like the mass of your robotic system, even though the sensitivity analysis aspect is a bit beyond the scope of this class. All right, so let's then move to today's lecture. So far I've talked about necessary optimality conditions, but oftentimes it's quite unwieldy to compute all the points that satisfy the condition gradient equal to 0. So we're interested in computational methods that directly give us a candidate for optimality. So that's what we're going to see next. And then we're going to conclude the lecture by expanding what we know from the field of unconstrained nonlinear optimization to the setting where we have constraints. Constraints are indeed something we have to deal with in this class, because at the minimum, we have one constraint we have to deal with, which is the basic constraints we have to deal with. The dynamics of our body. I mean, of course, we cannot go at the speed of light, so that's a constraint on our motion. So we can optimize as much as we want, but if you have a Fiat 500, you don't get the performance of a Ferrari. So that's probably an unfortunate fact of life. So yeah, so at least there is dynamics as a constraint. Okay, so let's talk a little bit about computational methods. Of course, this class will be quite deep in computational methods to solve optimal control problems, and what we're going to discuss now, again, is quite pedagogical with respect to what we're going to discuss next. And particularly, I mean, there are many different ways to attempt to solve a nonlinear optimization problem, but the specific way we look at is referred to as gradient methods, which is a particular class of iterative methods. So what are iterative methods? So the idea is that we want to solve our unconstrained nonlinear optimization problem, and we want to see whether we can find some rule that, starting from, do I use this superscript? Yes. Starting from some initial guess of what a local minimum could be. If you have no idea, you can just say, well, your local guess is 0, 0, 0, 0, 0, just the origin. Then you start producing a sequence of updated guesses. And the idea is that you hope that you have a rule that allows you to update your guesses in such a way that f of x0 is greater than of f of x1 is greater than or equal f of x2, ... So basically, you try to iteratively update your guess about what a local minimum can be, with a property that at every new guess, the value of the function is below the value of the functions of the previous guess, with a hope that after sufficiently many updates, the value of the function has been reduced so much that you have either reached a local minimum, or at least you are very close to a local minimum. But the question, of course, is how do you produce such a rule that allows you to go through these iterates, and in doing so, you decrease the value of the function. So for that, we again use the notion of tailored series approximation, or first order approximation of a function. Specifically, let's assume that our current guess is x, some vector, with components taking value 1, 3, minus 2, or 1, and assignment. So let's consider the updated guess obtained by taking x and subtracting alpha times gradient of f evaluated at x. I call this new guess as X alpha. It is parameterized by alpha. Alpha is a positive number. So basically, I am at X, so assume that you are in the plane. You are in the plane, so this is X. This is gradient of F. Remember that the gradient is a vector. So X plus gradient of F leads you here. But of course, this is parameterized by alpha. So the larger the alpha, the more far away you move from X. Okay, so then right here. Okay, so I call it X of alpha. So then we know that F of X of alpha, if alpha is small enough, so I don't move too far away from X, is equal to F of X, or at least approximately equal to F of X, plus gradient of F of X times X alpha minus X. But X alpha minus X is equal to minus alpha gradient of F of X. So what we got is that this is equal to F of X minus alpha gradient of F of X. Here there is a prime gradient of F of X. But you know that for any vector V in Rn, V scalar product with V is equal to the square norm of V. So this is equal to F of X minus alpha gradient of F of X square. The norm is a non-negative number. In particular, if the gradient is equal to 0, well, you already know that you are a candidate local minimum. But if this is not equal to 0, then this number is positive, which means that this number is negative, which means that F of X alpha has a lower value than F of X. So I've actually found a direction that leads me to a value for F that is lower than the value that I have at the current guess. Now, interestingly, as alpha gets larger and larger, which means that I move farther and farther away from X, this becomes larger and larger, which means that F of X alpha becomes smaller and smaller. So you might be tempted to say, so why don't you shoot alpha to a very large number? Why? You don't do that? I mean, it's tempting, right? Why don't we choose alpha equal 1,000,000? What's that?
Let's skip over the minimum.
Well, from this mathematics, there is nothing that is telling us that is skipping over the minimum. We just can arbitrarily decrease the value of the function.
Third approximation more toward
Exactly, which actually is related to what you were saying. That when we do the approximation, the first order approximation, always keep in mind that this holds true for points that are very close to X. So the moment that you move farther away, you might think that you're doing something useful, but in reality, you're not relying on an approximation that is telling you nothing about the value of the function. So the result will no longer be applicable. Make sense? Effectively, it means that you go maybe overshoot a local minimum. But mathematically, one must say, well, if the approximation was true, actually, you could just arbitrarily decrease the value of the function. So this leads us to the class of gradient methods. The class of gradient methods is a bit broader in that you can slightly generalize this construction, but just saying by looking at update rules, whereby x of alpha is more generally defined as x plus alpha d, where the gradient of f at x scalar product with the direction d, so this is a vector, is greater than 0. Is less than 0. Of course, if d is equal to the minus of the gradient, which is exactly what we have here, automatically this is verified. But my point here is that you don't need to necessarily go along the gradient direction. You can also pick some other vector as long as this property is satisfied. Because if you do so and you go through the same steps, again, you'll find out that f of x alpha has lower value than f of x, because the scalar product, the direction d is chosen such that this scalar product is negative. So geometrically, what is happening here? It's always good to have a little bit of a geometric intuition. So say that you have a function defined on the real plane, so on the plane of the board. And let's consider the so-called level set curves. So basically the set of points x, such as f of x is equal to a given number c. And then you can change the number. C is equal to 1, 2, and so on. So this could be, for example, the level set curves. So this will be f of x equal c3, this one. F of x equals c2. F of x, so for this one. F of x equals c1 for this one. And assume that the c3 is greater than c2, is greater than c1, and so on. So say that we are here at x. As you should know, otherwise you should look at the proof, the gradient of a function is orthogonal to the level set curves. So basically what this update rule is telling me is that I'm looking at moving along these directions here, parameterized by alpha. Or I can look at some other directions, like these ones, as long as the scalar product is negative, which means that I form an angle greater than 90 degrees. So this leads us to the celebrated class of gradient methods. Iterative rules whereby your next guess, so your guess of what a local minimum is at the iteration k plus 1 is equal to your previous guess after k iterations plus alpha k dk. Alpha k here doesn't mean alpha to the power of k. Here it just means that the step size, as we will see in a second, might change in value depending on which iteration you are at. So if the gradient is different from 0 and dk is chosen such that the angle between dk and the gradient is greater than 90 degrees, and the step size alpha is chosen to be positive, this is guaranteed to be, and alpha is chosen carefully, as we'll discuss in a second, this will lead to descent. Does it make sense? So gradient methods, again, iterative algorithms where you update your guess according to this rule, where the dk is a vector with a property that the scalar product with a gradient is less than 0, and the step size alpha is chosen to be positive. And typically we want to choose alpha such that the value at the new guess is below the value at the previous guess. Practically, you want to be careful that you don't choose alpha too big.
Does the guarantee still hold if we take into account the set order time?
Yes, this will lead us to, so you can reason also the level of, so there are two things. You can still use information from the Hessian, as we will see in a second, or you can find more sophisticated algorithms that consider more sophisticated approximations. We're going to look at the former. So I'll show you in 1 second why actually we want to use information also from the Hessian, not just from the gradient. So of course, there are two things that are unresolved yet. So how do you pick the descent direction? We said that the gradient is a choice, but really any vector d, as long as the scalar product with the gradient is less than 0, is a valid choice. So which one do you pick? And how do you pick alpha? So alpha is this number here, which is referred to as the step size. So for the descent direction, a popular class of descent directions is defined as the gradient pre-multiplied by a matrix that is positive definite. Of course, with this choice of the descent direction, the scalar product between the gradient of f and d is negative because we've chosen d to be positive definite and we have a minus in front. So this is a valid assignment of the descent direction according to our rules. But I just shifted the problem. So how do we pick the direction? Now the question is, how do I pick this matrix D? Two popular choices are you pick D simply as the identity. So basically you just move along the negative gradient direction. Or you pick D, as we were discussing with your colleague, as the inverse of the Hessian. Let me provide some intuition about why we may want to consider different choices of D without going too much into the details about how one would derive, actually, these rules. Specifically, let's assume that we have a function still defined in 2D with a very nice level set curves. So they're just circles. So this is the domain of the function, x1 and x2. So the function would have values that go orthogonal to the blackboard, and it will be a sort of a ball, right? Isotropic ball. So say that you're here, so the gradient shoots in this direction, is orthogonal to the level set curve. Clearly, this is the minimum because we're talking about a ball, so the ball is really at, so basically the function would be x1 squared plus x2 squared. The minimum will be at the origin. So you move toward the negative direction of the gradient. It's clear that you're pointing in the right direction. You pick some alpha, maybe you end up here. Then you recompute the gradient, maybe you end up here, and then finally you end up here. Great. But what if we are in a situation like the following, whereby our function is still defined on 2 dimensions, but now the level set curves are ellipses. So it's still a ball, but now is elongated in one direction and shrunk in the other direction. So say that you are here. Now the gradient points in this direction, and the negative gradient points in this direction. So as you see, actually you're not pointing directly to the minimum. The minimum is still 0. It's still a ball. It's just as it's elongated in this direction and shrunk in the lateral direction. So this is to say that picking as a descent direction the negative gradient may not necessarily be the best thing to do, especially if you have a level set curves that are very elongated. What happens is that you will start zigzagging a lot. So that, and here I'm just giving you the motivation, there could be a little bit of derivation to do it. That's why you may want to use the Hessian. Intuitively, the Hessian gives you information about the curvature of your function. So it allows you to better inform the direction that looks most promising in terms of going to a minimum. So basically it allows you to recognize that this problem is different from this problem, so you should do something different. That's roughly speaking what this Hessian here I'm doing. I won't go further into the details since this is not a class on linear optimization. Just to speak, there are different choices. This seems better. Of course, it uses more information. It uses information about the curvature of the function, but everything comes at a cost. Here, the cost is that if you want to implement this descent direction, not only you have to compute a gradient, but you also have to compute a Hessian, so basically a matrix of second-order derivatives. Depending on the size of your nonlinear optimization problem, maybe there is not enough bang for the buck. Sure, you might decrease the number of iterations because your direction is better aligned with where the local minimum eventually will be. But every iteration is much more expensive. So this is just to say that, and we'll see this theme over and over, that there is a little bit of a trade-off in terms of how much sophistication you want to have in your algorithm versus the algorithm that eventually you end up using, since eventually your goal is to get to the local minimum as fast as possible. So we talked a little bit about descent direction. What about alpha, the step size? Again, different ways of choosing a step size. For example, a possible way is the so-called minimization rule. Among all the positive alphas, you choose the one that leads you to the largest cost reduction into your function f. Sensible, but you have to solve a minimization problem. Not terrible, minimizing over a scalar, but still, it's a minimization problem that you want to solve. At the other end of the spectrum, you're super lazy. So you just pick a number for alpha, say 0.1, you stick with it. It's probably the very first descent algorithm that you would implement. You just pick a value for alpha, you stick with it, and you hope for the best. Unfortunately, though, with this choice, actually the method might diverge, so it might not converge to a local minimum, and the convergence rate could be very slow. So another idea that is quite popular is the so-called diminishing step size. So you choose an alpha that across iterations goes to 0. So you start with 1, maybe 0.5, 0.1, 0.005. So basically you have a rule whereby alpha goes to 0, but with a property that the sum over all alphas across iteration is equal to infinity. So what's the idea here? The idea here is that oftentimes, when you start the process, you are, so let's look at now a one-dimensional problem. So you're here, so you're quite far from the local minimum. So at the beginning, it's quite typical to have long step sizes. So you make like a big jump, and maybe you move here, then you move here. Maybe then you overshoot. But then after a while, where conceivably you have gotten closer to local minimum, you start making smaller and smaller jumps so that you don't oscillate too much around the local minimum, and eventually you converge to it. So at the beginning, very large alpha so that you can make big progress. But the point with large alpha is that as you get close to the local minimum, you can start bouncing around and oscillating. But then you start decreasing the alpha so that you do that final fine-tuning to really get to the local minimum you care about. But you have to be careful, because if your alpha goes to 0 too quickly, maybe you don't make enough steps toward your local minimum. So you want to make sure that collectively, when you sum all of the alpha, actually you may make potentially an infinite distance, so that you're guaranteed to explore widely if necessary. In the first iteration, generally pure guess. Yeah, there is quite a bit of hyperparameter tuning. Which is a good segue into this analysis. So there is a lot of stuff that we haven't discussed. How do you choose those parameters? So for the descent direction is a little bit more principle. For step size is a bit murky, is a bit more experience. But in general, there are three key concepts we haven't really discussed. The first one is, how do we guarantee that this algorithm indeed converges? So I told you how in one step, you're guaranteed to decrease the value of the function. But that doesn't mean necessarily that you're guaranteed to get to the local minimum once you iterate across all of the iterations. So indeed, there are some properties that one could list that ensure that you converge to a local minimum. That is, to a stationary point. That means a point where the gradient is equal to 0. Second, when do you stop? There are different termination rules. One might just say, I'm willing to invest 100 iterations, whatever I get after 100 iterations, that's it. Or maybe you look at the value of the function at xk plus 1, and the value of the function at xk. You take the difference. If this difference is less than epsilon, you just quit and call it a day. It means that you're not doing much progress anymore. And so there is no point in keeping investing computation. And then convergence rate. So depending on the initial condition and how actually you choose the step size profile, what can you say about how quickly it will converge to a stationary point? We could spend pretty much half of the class on this topic, so we are skipping on those, but I just want you to be aware of those. And second of all, the class of methods that I just discussed are referred to as gradient methods because you use information for the gradient, but there are also methods that do not need or necessarily need information from the gradient. Those are referred to as derivative-free methods, such as the coordinate descent method that iteratively minimizes along the coordinate directions to find the minimum of a function, or the Nelder-Mead method that is another clever method that doesn't require at all any computation of derivatives. This is just to say that there is very rich literature both in the field of gradient-free and non-gradient-free methods. Any questions? Right. So far we've talked about unconstrained nonlinear optimization problems. But we are particularly interested in constrained optimization problems because, as I said, optimal control problems typically have at least one constraint, which is represented by the dynamics. As we will see, the key solution to solve the constrained optimization problems boils down to the concept of a Lagrange multiplier. And actually, this concept will carry over also to the setting of optimal control. And we won't do proofs here, but just wanted to give some intuition about how people will go about proving statements about equality constraints problem or inequality constraint problems. And typically, there are two main approaches. The first one is the so-called penalty viewpoint, whereby you take the constraints, you put those constraints, if you so to speak, in a cost function, and you assign a high penalty for violating them. So basically, you reduce a constraint problem into an unconstrained one, where constraint satisfaction is viewed as a penalty cost, meaning that if you satisfy the constraint, then you have 0 in the cost. If you don't satisfy the constraint, then the cost shoots up. That's one way. Or the other way is to take an approach similar to the one we have discussed in the case of unconstrained optimization. But when we talk about displacement, we can't talk about arbitrary displacement anymore because some directions are allowed, some others are not, because we have equality constraints. So we have to have a little more sophisticated notion of what an allowable displacement is, and based on that derive necessary optimality conditions. So let's start first with the equality constraints. So equality constraint optimization problems are those whereby you're still trying to minimize a function f over real n, so over n decision variables, subject to m equality constraints, written as hi x equals 0. And we have m of these functions. As I said, f maps Rn into R, and hi also map Rn into R. And here we assume that they are both continuously differentiable. And just to save on some notation, I will compactly write the set of function h1 to hm as bold h. In general, in this class, a bold phase means vector. So the basic result in the field of equality constraint problems is the Lagrange multiplier theorem. That is a bit cryptic, and I will provide some intuition later on. But mechanically, it states that if x star is a local minimum, Then there exist m numbers. M is the same number of the equality constraints. These numbers are referred to as the Lagrange multipliers and denoted as lambda 1, lambda 2, all the way to lambda m, such that the gradient of f plus the linear combination of the constraint gradients scaled by the Lagrange multipliers, 1 per constraint, is equal to 0. I'll provide later a bit of justification. Right now, this seems a bit mysterious. But first, let me show you the mechanics about how people use this theorem. So before, in unconstrained optimization, you take the function, you compute the gradient equal to 0, you find the points that satisfy the condition, and then among those points, you see which one achieves lowest value. Great. Here, we do something similar, but we don't just set the gradient equal to 0. That would be the case. Look how, if the number of constraints is equal to 0, this piece goes away, so we recover the condition gradient equal to 0. Here is a refinement. It's not just gradient equal to 0, it's gradient plus the linear combination of the constraint gradient being equal to 0. What does that mean in practice? So let's assume that we have this optimization problem, which is a quality constraint. This is the objective function, and this is the constraint set. So essentially, the function that we are looking at so this is the plane, x1, x2. So now the function is not mapping any possible point into a value, but only those points that belong to the circle. So this is the locus of points whereby x1 square plus x2 square equal 2. So this is basically the feasible domain. You can pick any point in here, and you want to find the one for which f, namely x1 plus x2, achieves lowest value. So mechanically, what do? This is a necessary optimality condition, so you treat it the same way as the gradient equal to 0. But now there is that additional term that you have to account for, and note that you also have to solve for those Lagrange multipliers. So what you do is, first, you compute the gradient of f. Ideas of what the gradient of f is for a generic point x1, x2? Should I ask the CA? And joke. So it's 1, 1. Right? Because this, remember that the gradient is, by definition, gradient of f with respect to x1, gradient of f with respect to x2. But f is equal to x1 plus x2. So the derivative of x1 plus x2 with respect to x1 is equal to 1. Derivative of x1 plus x2 with respect to x2 is equal to 1. Okay. So then what is the gradient of h? So derivative of x1 square plus x2 square minus 2 with respect to x1 is equal to 2x1. And for the other component, it's just 2x2. So then what you do is that you put everything together. And so the Lagrange multiplier theorem, it says that if x is a minimum, then 1, 1 plus lambda. Here we only have one constraint. So we're going to have only one Lagrange multiplier, which I call lambda. Lambda 2x1, 2x2 is equal to 0. And I have to solve for x1, x2, and lambda. Once I solve for x1, x2, and lambda, I don't care about lambda anymore. That was just a mechanism for me to find the necessary optimality condition for x1, x2. I only look at the x1, x2 that have derived. But 2 equations, 3 unknowns. That's a problem. Do you have an idea where the last equation can come from? Equation can come from? Exactly. So still the necessary optimality condition says that x has to satisfy this condition. And of course, x has to be feasible. So it has to belong to this circle. So we also have the additional equations x1 squared plus x2 squared equal 2. Okay. So now we just had to solve all of this. So we have 1 plus 2 lambda x1 equals 0. 1 plus 2 lambda x2 equals 0, which means x1 is equal to minus over 1 over 2 lambda, and x2 is equal to minus 1 over 2 lambda. Now I plug x1 and x2 in here so that I can solve for lambda. So when I plug into the constraint, so what I get is 1 over 4 lambda squared plus 1 over 4 lambda squared equal 2, which implies 2 over 4 lambda squared equal 2. So this goes away. So lambda is equal to plus minus 1/2. And then I go back here, and what I get is so if lambda is equal to 1/2, then x1 is equal to minus 1, and x2 is equal to minus 1. And if lambda is equal to minus 1/2, then x1 is equal to 1, and x2 is equal to 1. For which value the function achieves, for which pair the function achieves lower value? Here. So that's a minimum. Actually, the Lagrangian multiplier does have value, but at least for the way I'm presenting it here, it's just a means to an end. So we use it to solve for these equations, but then once we get to our local minima, we just throw it away. So it's just the mechanics. Now I'm going to give you a bit of intuition about that, how this works. So think about gradient equal to 0, but now there is this additional sophistication where you also have to account for the constraint gradients, and you go back through the notion of Lagrange multipliers that are additional variables that you solve for. The good news, though, is that between the Lagrange multiplier theorem and the equality constraints, you have the same number of variables as equations, so you can always solve for all of that. Of course, it can be challenging because these might be nonlinear algebraic equations. Let's look graphically at what's happening here, and I'll come back to this picture. So this is your feasible set, and these are the level set curves for your cost function. Remember that the cost function is f x1 plus x2. So x1 plus x2 equals c defines a line in the x1, x2 space, namely the line x2 equal c minus x1. So the one that goes through the origin will be x2 equal minus x1. As I go in this direction, I actually have increasing values. So this will be x1 plus x2 equal 3 or 4, 5, and so on. And so on. So from this interpretation, and you'll see later in a second why this is useful, remember that the optimal point, as we found it, is minus 1, minus 1. So that's a minimum, which makes sense because these are the level set. And we want to try to pick the level set curve with the lowest possible value, but it still intersects the visible set. So as you move, you move, you move, until you get here at the point of tangency. Here, there is no point x1 and x2 that will be feasible with respect to the circle. The objective would actually get a lower value, but it's not allowed. Does it make sense? Maybe? Think a little bit about this geometric intuition because it's important. So again, this is the constraint set. These are the level set curves. And this will be the set of points such as x1 plus x2 is equal 5. x1 plus x2 is equal 3. x1 plus x2 equals 0. That will be this curve here. And here I have 2 points for which x1 plus x2 equals 0. The one here and the one. But I can go even further. So x1 plus x2 equals minus 1. And so on until I get here, which is x1 plus x2 equals minus 2. And I have an intersection here. So there is at least one point that achieves that value. If I go further down, then there is no point that, yeah.
Is there a geometric interpretation of why we get 2 lambdas? Is that the max min?
Yes, because because remember that this is just a necessary condition for a stationary point. So it's not differentiating between it being a maximum and minimum. And in fact, if you plug in the other lambda, you get a maximum here.
If we had lambda equal to 0, would that mean that the constraint was not important for the
the constraint is always important for the minimization because you're only allowed to pick point from the feasible set. But
lambda equals 0, what does that mean?
Lambda equals 0. But remember that here, the condition is not in terms of the quality constraints, is in terms of the constraint gradients. So that's why lambda equals 0 per se doesn't tell you immediately a condition on the quality constraint per se, because this is with respect to the gradient of the constraint. But related to that, let's try to be a little bit more of intuition. And essentially, there are 2 ways, at least in my mind, to interpret the Lagrange multiplier theorem. So let's look. Let's look at a simple case where you have only one constraint. Yeah. I just, for simplicity, avoided the parenthesis x. So what the Lagrange multiplier theorem is telling us is that the gradient of f belongs to the subspace spanned by the constraint gradients at x. That is, the constraint solution will be at the point of tangency of the constraint cost curves and the constraint function. What does that mean? So here, what the Lagrange multiplier theorem is saying is that the gradient of f is equal to the gradient at the candidate for optimality. The gradient of f is equal to the gradient of h times a scalar. So basically, they are collinear. But remember that the gradients are orthogonal to the level set curves, which means that if the gradient of the level set curve refer to the constraint set, and the gradient to the objective function are collinear, it means that those 2 level set curves are tangent to each other, which is really what you have here. So this is the situation. So we have the circle, which is the feasible set. Here we have the point minus 1, minus 1. The gradient was the gradient of the objective function was 1, 1. And the gradient of h here is equal to minus 2, minus 2. So you see that the gradient of the objective function and the gradient of the constraint set are collinear, which means that the level set, well, the constraint set and the level set carved for the objective function are tangent to each other, which notionally captures the fact that to minimize, you're trying to push your level set curve for the objective function as much as possible towards some situation whereby if you push farther, you don't have intersection anymore with your constraint set. If you could push it even farther, then you would do so. Tangency is basically the geometric notion that captures the fact that you cannot push it farther. Some intuition here, but it's actually correct intuition. Make sense? So that's the more geometric intuition. The other way that I like to think about Lagrange multipliers is as follows. They might sound a little bit cryptic, but actually it's even clearer, in my opinion. So the cost gradient, so what the Lagrange multiplier theorem is saying, remember, is saying that the gradient of the cost function at a local minimum is a linear combination of the gradient of the constraints. So what that implies, and we'll see in a second. So first let me state it, and then I'll explain it. What that implies is that the cost gradient, gradient of f is orthogonal to the subspace of first order feasible variations. We define the feasible variations as those variations that are orthogonal to the constraint gradients. So what is it saying? So V of x star is the space of displacements that are allowable up to first order, meaning that they lead you to a point that is still feasible up to first order. Specifically, h of x stars plus delta x is equal to h of x star plus gradient of h times evaluated x star times delta x. So if you choose delta x from this set, then this term is equal to 0. This term is also equal to 0 because we're assuming that x star is feasible since it's a Candy local minimum, which means that this is also equal to 0. So all this is to say that if you move along these displacements, you are moving away from x star to new points that at least up to first order satisfy the constraints. But remember, but then if that is true, then delta f of x star times delta x is equal to 0, thanks to the Lagrange multiplier theorem. Since the gradient of f is a linear combination of all these constraint gradients, and the delta x is picked in such a way that the scalar product between delta x and each one of these constraint gradients is equal to 0, then I'm just, if I replace with the lambda i's gradient of h i's, all of this goes to 0. So what I'm saying here is that you can view the Lagrange multiplier theorem as essentially embodying the conditions whereby the gradient of f has to be orthogonal to the space of feasible variations, which is exactly what we had in the case of unconstrained optimization, if you remember. And then we said that delta x can be anything, and that leads to the condition gradient equal to 0. Here, delta x cannot be anything. Delta x has to be taken from this set here, and so the condition is a bit more sophisticated. It's saying that the gradient of f, the most we can say, has to be orthogonal to all these delta x. I mean, my point here is that what we're doing is just a more sophisticated way of what we did before with unconstrained optimization, but now we have to be more sophisticated in the sense that we cannot reason about all possible displacement, only those that satisfy the equality constraints up to first order. So this leads us to the key result here, and we will see this result showing up again, of course, with some modifications in optimal control, which is a necessary optimality condition for equality constraint problems. So let's assume that x star is a local minimum of f subject to h of x equals 0. And assume, and that's a technical condition, that the constraint gradients are linearly independent. Turns out that if it is not the case, actually this is no longer a necessary optimality condition. I don't want to elaborate too much on this condition. Main point is that always check that for a candidate of optimality, the constraint gradients are linearly independent. Then there exists a unique vector, lambda 1, lambda m, called a Lagrange multiplier vector, such as the gradient of f is a linear combination of the constraint gradients. So a feasible vector for which the constraint gradients are linearly independent is called regular. How do we prove this theorem? It's actually a little bit convoluted, but essentially can be proved in a couple of ways. First, again, as we said before, penalty approach. We move the constraints to the cost function. We penalize deviations from feasibility. And then we make a limit argument to derive the Lagrange multiplier theorem. Or, and this may be a little bit more direct and intuitive, but actually it's a bit, not convoluted, but it's a little bit more annoying in terms of bookkeeping. So what you do is that you have n variables and m equality constraints. So you express m of the variables in terms of the remaining n minus m. And then you reduce the problem to an unconstrained optimization problem. And then you do 3 pages of analysis. But just saying, what the intuition comes from. An excellent book, if you're interested in nonlinear optimization, is the book of Dimitri Bertsikas, Nonlinear Optimization. If you want to learn more about convergence rates for gradient descent methods, proofs of Lagrange multiplier theorems, explore a little bit more these technical conditions and so on. Mnemonically, and this is again something that will come back in optimal control, what you do with with equality constraint problems is to form the so-called Lagrangian function. The Lagrangian function is a function that comprises your objective, plus you now lift your equality constraint into the cost, and you scale down by multipliers lambda I, which are additional variables you have to find. And then you just treat the problem as an unconstrained optimization problem with respect to this augmented cost function. So then the necessary optimality condition with respect to the Lagrangian becomes set the Lagrangian L equal to 0, as if the problem was unconstrained. And what you get when you take the gradient with respect to the x variables, you get exactly the Lagrange multiplier theorem. So gradient of f plus sum of lambda i's gradient of hi is equal to 0. When you take the gradient with respect to the lambdas, you get the different condition h1 equals 0, h2 equals 0, and so on and so forth. Notably, the gradient with respect to x leads to a set of n equations. The gradient with respect to lambda leads to a set of m equations. And we have n plus m variables. So we have n plus m variables over n plus m equations, so you can solve for that. So that's what I wanted to say about equality constraint problems. Next time, we'll have a quick look, and this will be quite brief, at the inequality constraint case, which will lead to the so-called KKT conditions. And then we'll move into our first topic related to optimal control.